Welcome to DSE FIU's second ever advanced problem video. In this video we're going to be going over a problem called H index 2. So what does the problem entail? Well, let's read the problem. Given an array of citations sorted in ascending order where each citation is a non-negative integer, so for instance, if you start all the numbers in the array will be greater than the last one in the array. That's all that means. Write a function to compute the H index. So what is an H index? According to the definition, it says that there is a specific index H. So H is an index in our general array, and it'll be based on the amount of n papers. So the n is standing for the amount of stuff that's in the array. So if we're looking at the first example, there's 5 stuff, so n will equal be 5, or 5 papers in this case, since papers is relating to a research paper, and an H index shows how important this researcher is. So that's all that means, and that's based on the amount of citations, which are the values of the array. They have at least 8 citations, and the other n minus h papers have no more than 8 citations each. So what does this exactly mean? It took me a while to understand it, but I think it's best to show it on a whiteboard here. So here we have the example, and we have different values of what h could be. You'll notice that h, so there's different values here. There's h equals 1, 2, 3, 4, 5. But the values of h don't exactly equal the values that are in the array, because remember, h is dependent on the indices of the array. So let's figure out what our h index would be for this array. For just showing this as an example, so we have our array here, and we have different possible values of h. It says that for an h index to be the h index, it's required that there must be at least this amount of this value in our array. So let's go for our first one. So there must be at least one value, or there must be at least one value with that are greater than or equal to 1. Is that the case here? So is there the amount of values greater than equal to 1? Is there a certain number? Well, there is, because they have 1, and then there's 2, 3, 4, 5. All of these numbers, there's at least a number is greater than or equal to 1. So we can go ahead and that could be an answer. But we want, the thing is with this problem is that we want to get the maximum value. So let's go ahead, let's keep checking. So let's start with 2. Is there are there enough values so that are there at least 2 values that are greater than or equal to 2? So we go here, 1, 2. There's at least 2, and they follow the rest of this array. So we go ahead, and that is true. So actually, because of that, there is a possible h index of 1. There's also a possible h index of 2. Now let's go ahead and see, is there a certain amount of, are there at least 3 values that are greater than or equal to 3? We'll go here, we'll say there's 3, 5, and 6. So therefore, there's 3 of these numbers here, so this is true, and therefore there is also an h index of 3. Now, is there an h index of 4? Let's see. Are there at least 4 numbers greater than or equal to 4? We'll look here and say greater than, well, this number is 5 is greater than or equal to 4. So this number is, and this number is. But the size of these numbers is 2. So therefore, this number is not an h index. And we could also do the same for 5. Like, are there at least 5 numbers that are greater than or equal to 5? We'll see 5 and 6. There's these numbers here, but then again, there aren't 5 numbers that are greater than or equal to 5. So therefore, 5 is not an h index. So therefore, you have multiple h values here, but you want to return the value with the greatest h index. So therefore, you return 3. Give me a second. Okay, that malfunctioned for a second. All I meant to do was this. You get the point. So yeah, we return 3. So that approach that I actually did, going through certain values of h and then comparing them with the rest of the array, this was actually an O of n approach that I took. So this was a linear approach which was O of n. So this is one possible way to solve the problem. But we look at the problem description, and it asks us if we can do this in logarithmic time complexity. Is there a possible way to do this in logarithmic time complexity? Well, truth be told, there is. How is that possible, right? So let's take a look here. So we have our original array. Okay, so we're talking about logarithmic time complexity. So a logarithmic time complexity would be, it's happening again. My apologies, guys. Still getting used to the pen. A logarithmic approach would be O of n, or log n, log of n. How can we find this? How can we get something like this, where the approach that you take is not just going through from left to right, it would be cutting half different parts of the array. The only way, one of the main ways to do that is through binary search. So how can we use binary search to solve this problem? So we have our array here. Let's imagine, so we want to find the maximum value with the greatest h index. So how can we do this, right? Imagine, let's just start from the middle, and let's find let's just take binary search in general to find our h index. So let's start with 3, right? Let's start in the middle, or let's say we have our original array. I'll write it back down here. 3, 5, 6. Right. Let's start with 3. We want to determine whether this value, or let's say n minus h at this point would be 3, right? So it would be 3. We want to ensure that we have the highest possible value. So okay, if we start here, we know that this could be a possible big value. We know that the n minus h, so n, where n is the length of array, and where we have h as a specific point. So at this point, it's going to be 0, 1, 2. The value, so it's going to be the specific point is 2. So we do let's say this, well, this is going to be I equals 2, n minus I or which is also the mid, which is going to be you have it like that, right? So h will be 3 at this point. Hypothetically, if the h is equal to 3, and you have your value here, 3 is being equal to that, then there's actually no better way to get it better than this. So you will actually end up returning 3. So 3 will be your answer, or the more so the h index 3 will be your answer. But let's say we had a different array. Let's say that let's say 3 wasn't in the array. Imagine we had 1, 2, 5, 6. So let's do traditional binary search here. I'm gonna use a different pen color. Let's do so let's say because with binary search we have to have a low and we have a high. So low will equal 0 and high will equal the last element. So that'll be let's say this is also, let's call this ar dot len -1. Let's also keep a track of n and make that equal to ar dot len. So we have our values here. So let's go ahead and take the middle. What is the mid at this specific point, right? The mid is equal to low plus high minus low plus, I'll divide it by 2, my apologies. And the value of that will actually be 0 plus the len -1. It's gonna be 3 and minus 0 divided by 2. So mid equals 1, because 3 divided by 2 with integer division will be 1, and 1 plus 0 is 1, so that's why it will be that. So mid, we're gonna go off based off our indices. So 2, right? So this is, we did with indices talking is 0, 1, 2, 3. We have 2, and we have to check whether this h index would be good. Let's also keep in mind that low, high. This might be kind of confusing. So clear up our space a little bit. So we have low and high, and this is our mid at the moment. So we're gonna go ahead and check whether this element will work. So are there at least 2 elements that are greater than or equal to 2? We will go ahead and check and see. Well, 0 and 1. Are there at least 2 elements that are greater than or equal to 1? Greater than or equal to 2. We'll go ahead and see that, with this actual specific index, that is possible. So we can maybe keep 2 in mind for now, but we want to go ahead and see like the highest possible number. So because 2 is a possible value, we're gonna actually start looking more to the right hand side. So 2 as a number works. But now we're gonna go ahead and switch our AR. So we're actually gonna stop looking at this side. We're gonna start looking more So low actually now becomes low will now go here. So now our new mid is equal to 0, 1, 2 plus, so mid equals 2 plus 0 divided by 2 is 0, which equals 2. So mid 0, 1, 2 here. So let's look at 5. Are there 5 numbers greater than or equal to 5? It's not possible. So we're gonna go ahead and just return, well, or at least 5 won't work. So yeah, 5 won't work. So therefore, we're gonna go ahead and we're gonna try to find a number that's possibly smaller, or an indices that's smaller. So we're gonna go ahead and change our high. What is high going to be? High will be it will be the mid minus 1. So high will actually go here. But then we have high is less than low, which is not correct, which we don't want. So therefore, we're just going to return whatever n was minus low. So in this case, we have n is equal to 4, low is 2, and then we return 2. And 2 will be our answer. So that's how that's how you get the answer using binary search. If by chance, you know, with this example, since 3 exactly worked out, you know, that was perfect. But because 3 was there were exactly three places left with the number 3, so that exactly works. But with this other case, it didn't exactly work. So let's go ahead and code that up. Okay. Okay, so let's just code. So we're gonna have an int low equals 0, int high equals citations length minus 1, and like I mentioned, we're gonna need an n to use because it'll just make our code a lot simpler. So then we're gonna have while. So basically what we were doing could have been done in a while loop, because we'll keep iterating over and over and over while the low is less than or equal to high. So and it's fine also if the low is equal to the high, since it doesn't really matter if they're the same number. Like if low and high are by chance the same, you could still check that value for the mid and see if it's an H index. But if you have the high is less than the low, then you've already most likely seen like all the possible values that could be great H indexes that would work. So let's go ahead and see. So we also have, so now we have to make our int mid, which is low plus, also I'm doing this in Java too, so this is a Java implementation, although what I wrote in could be done using Python or any language you're doing. So we're going to first check if the indices are going to be equal. Like for instance, our H index and our indices is equal. The thing at the specific point is equal. So if citations at mid, is equivalent to n minus mid, then return the return mid, or n minus mid, more so. Else if, so we came up with a few different cases. If the low, there's the three other test cases, or I mean, sorry, two other test cases. Also, if citations at mid is, so if it's less than, right? When are we going to get less than? So that's if this specific value, so we're like, let's for instance say like 2 is less than the potential. So 2 minus n minus mid is at this point I'm looking at here would be equivalent to 5 minus 2 is 3. So there is possible values where it could be greater. So you want to not gonna return anything. You want to increase your, you want to keep looking forward to see what's possible. So you would do mid plus 1. Otherwise, else high equals mid minus 1. And by chance, if high is becoming less than low, then you return the n minus low. Yep, that's exactly how you do h-index 2. Thank you all so much for your attention, and see you in the next video. If you also want to keep a track with our problems and stay engaged with competitive programming and be the best programmer that you can be, the link to the Discord and all of our channels for DSCFIU will be down below. And make sure to join up everything so that you can stay engaged with our community. Thank you so much.